I'm going to talk about solving non-homogeneous second-order differential equations using the method of undetermined coefficients. Non-homogeneous second-order differential equations have one thing more than homogeneous differential equations. Now, a homogeneous equation is something like y double prime plus y prime plus y is equal to 0. Here the coefficient of everything is 1. Here, here, here. Now to make this into non-homogeneous, we can replace this with a term depending only on the independent variable. So say I add e to the power t. Then my equation becomes y double prime plus y prime plus y is equal to e to the power t. This is now a non-homogeneous equation. To solve something like this using the method of undetermined coefficients requires we use two steps. The first step is to solve for the corresponding homogeneous equation. So in our case here, that will be y double prime plus y prime plus y is equal to 0. When you solve this and get a solution, something like y is equal to whatever, this is what we call the complementary solution. And it is regarded as yc. The second step is to find a particular solution which we regard as yp. Now, if we are able to do both of these, our final solution is just the sum of these two. Now, what really are these two different solutions? Now, the complementary solution is a general or a representation of the infinitely many solutions with arbitrary constants. So if you have a solution, say y is equal to b1 e to the power t, b1 can be any number, and there can be infinitely many numbers. So this is what is a complementary solution. Now, a particular solution for a specific independent variable term does not have any arbitrary constant. So this will be something like 4e to the power 2t. It's specific. I want you to keep in mind that this type of method only works if the independent variable term, the kind of term that we put here, is either an exponential, as in e to the power something. It's either sine something or cosine something, or it's a polynomial. This can be t times anything. Okay, now this is because we're going to guess what the particular solution will look like. And these are easy to predict. Let's see the business with an example. say we have y double prime minus 4y prime minus 12y is equal to e to the power t. First step is to solve the homogeneous equation. And if I use the characteristic equation, then solving this gives me 6 and negative 2. So my complementary solution is b1 e to the power 6t plus b2 e to the power negative 2t. And step number 2 is that we are going to guess that our particular solution is of the form a, which is some constant, times e to the power t. Now you let this thing, e to the power t, to be the same as what's given in the question, e to the power t. Because differentiation or integration of e to the power something has no effect on this thing. E to the power t or e to the power whatever it is remains the same. The coefficients do change. So that is what we're going to try to find. That is why we add this coefficient, hence the method of undetermined coefficients. So we want to plug in this solution into here. So since we have y double prime and y prime, let's do that here. So y prime of this is the same, and so is y double prime. Now if we put this here, we will get if you do this algebra, you will get negative 15a e to the power t is equal to e to the power t. I'm going to cancel these out. And I'm left with a is equal to negative 1 over 15. Which tells me that my yp is a e to the power t, which is negative 1 over 15 e to the power t. So my final solution is the sum of the particular and the complementary solution. So that is b1. We said it's to the power 6t plus b2 e to the power negative 2t minus 1 over 15 e to the power t. Let's do another example. Let's deal with polynomials. Again, first we're going to solve the homogeneous. I'm using the characteristic equation. Solving this should give me 3 and 2. So my complementary solution becomes b1 e to the power 3t plus b2 e to the power 2t. Second step, I'm going to assume that my particular solution is a times t squared plus bt plus c. So whenever you get a polynomial, what you're going to do is assume the same degree and then add a term until you reach t to the power 0, decreasing 1 t to the power 1 each time. Excuse me. So I had t squared here. So I start with t squared, then I decrease 1 becomes t, and t to the power 0 is 1. And all of these terms have an unknown constant. So there's one thing to keep in mind when doing polynomials, a very important thing. Stick till the end of the video to find out. But until then, we're going to differentiate this. And that's going to give us 2at plus b. And again, 2a. So putting these in here, we will get 2a minus 10at minus 5b plus 6at squared plus 6bt plus 6c is equal to 2t squared. I have just substituted these, and this for this, and this, and equated it to this. So now I'm just going to equate this and this because they have the same power of t. I'm going to equate this and this to 0 because I have 0 times t. And then I'm going to equate this, and this to also 0 because I have 0. The constants equal to add up to 0. So now these become 6a equals to 2. This tells me that a is 1 over 3. Negative 10a plus 6b is equal to 0, which tells me that b is equal to 5 over 9. 2a minus 5b plus 6c is equal to 0, which means c is equal to 19 over 54. You can use a calculator to solve all this. So if I substitute these a, b, and c right here, my particular solution becomes 1 over 3 t squared plus 5 over 9 t plus 19 over 54. So my final solution is the sum of the complementary and the particular. So this becomes b1 e to the power 3t plus b2 e to the power 2t plus 1 over 3 t squared plus 5 over 9 t plus 19 over 54. You guys can go ahead and solve this with me, and if you find any mistake in my algebra, do let me know in the comments. I hope there isn't. So now let me just give you a summary for assuming what the particular solutions should look like for different types of terms. So we have the exponential, the trig, sine or cos, and polynomials. So the thing I was talking about for polynomials is that when we are dealing with these, suppose, say, we have t squared. You guess at squared plus bt plus c, like I did above. But if the complementary solution has a term with, say, t in it, suppose if we had yc is equal to t, you have to multiply this thing, our assumption of the particular solution, by t squared. So that it can become a t to the power 4 plus bt cubed plus ct squared. The point is, you don't want your particular solution guess to have t power similar to the one seen in the complementary solution. Now, if we had kept our complementary solution assumption like this, then we have something here which is similar to what we have in the complementary solution. You will want to avoid that because you will run into issues.